I understand nothing. What's going on? Ah, 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 ah.
We have to wait until still
Ah,
2 minutes.
okay. No, no. Uh,
So we can start our next talk. The next speaker is Bruno Després, and the title of the talk is Scattering Structure of Linearized Vlasov-Poisson Equations. Please, Bruno, you can start.
Thank you very much. Thank you very much, of course, to Ricardo for the kind invitation for being part of this prestigious online conference. And also, I also have to say that I think I met Ricardo 30 years ago when I was a student, some long time ago. And very fortunately, perhaps 7 years ago, we started a scientific collaboration with Ricardo when he came in Paris. And for me, it really helped to solidify my understanding of scattering theory and the application to physical theories of all this series of unbounded operators. And thank you very much, Ricardo. So I will not say a word on the application to magnetize Vlasov equation because you already did. But instead, I will explain kind of for me the history of the application of these ideas to Vlasov-Poisson equation. So it is a work that has been done with Frédéric Charles, now professor, so Ricardo, Alexandre Réger and Victor Fournet are ex-PhD or PhD, and Christophe Buet is a researcher in France. Okay, so I have 3 parts. I have split my talk in 3 parts. In the first part, I will explain why I started, perhaps at the time when Ricardo came, to try to understand the connection between scattering theory that I like very much and what is known about the theory of all these linear Landau effects, that are well known. And there was some problem to understand, and this is what I will try to explain. So it is the first part. Then so it will be more establishing some structure connections between different theories. Then the second part will be a description of the most advanced result that I was able to prove. And as you will see, there will be also connection with very abstract, very, very fundamental result by famous people on the regularity of transport equations, because it will be a key ingredient. And then the new part, application to new transport equation. It will be new for you, Ricardo. It will be in the last part, so it will be an extension to new physics, but of the same ideas. Okay, so I start. So some years ago, I read this paper by Pierre de Gon, who did some some very rigorous mathematical analysis of the linearized Vlasov-Poisson equation. And in the conclusion of his paper, he noticed that there is an extremely strong analogy between his results and the one which are very classical in scattering theory, the Lax and Phillips scattering theory, but many others say, And I was very puzzled by this remark. Why? Okay, so essentially it is way how you describe the asymptotic behavior of a certain wave or certain dynamics for a long time. And I was very puzzled by this question because there are two things. Either it is an analogy, meaning it is similar but really different nevertheless, or it is the same just because we have not discovered the way to rewrite the equation in the convenient framework. This is exactly what I tried to, what puzzled me the most at that time. Okay? And as you will see, all my talk will be to advocate that it is not an analogy, it is an example if you write in good variables. Okay? So, okay, but nevertheless, there is a debate, and the classical linearized theory of Vlasov-Poisson equation is not done within scattering theory. Let's see. So my first part, I start with an example, very simple. I try to be as simple, so I need to describe everything. So it is a 1D, 1V. Why? Because you have a kinetic function F, which is the density of some particles, which are electrons here. They are charged particles. There will be an electric field. Very famous problem. And the particles are transported by their own velocity and by the force exerted by the electric field. And this is why you have this kinetic equation dtf plus v dxf minus e dv of f equals 0. F is a function of t, x, and v because a particle has a velocity. But there is a second variable, so v is a variable as x and t. But E is an electric field. And what you assume that you have a background of ions. So you have a fixed density of ions, rho ions. And if you subtract the charge of the electrons, all charge, elementary charge are set to 1, of course. Then you need to write the Poisson equation. So dx of E equal the difference of density. And it is the 1D, 1V nonlinear. It is nonlinear here at this stage, Vlasov-Poisson equation. There are plenty of basic properties. Of course, F needs to be non-negative initially, and because it is transported, you see along the characteristic, it is okay. It is preserved. But now what you do, you start to say, okay, what's going on if I try to analyze the dynamics around some important profiles? So of course, in plasma physics or in particle physics, an important profile is a Maxwellian. It is a standard distribution of the velocity of the particle. So it is my function exponential of minus v squared divided by 2. There is no temperature because it has been set to 1. And you can say, okay, I have an homogeneous profile, but actually, as you will see, there is an interest of introducing the density, reference density, n0 of x. So I decide that my stationary profile is f naught of x and v. So, okay, you play with the equation, so I will not spend time on that. And you see that if n naught is the exponential, we say that the electrons are Boltzmannian of the electric potential, and then E0 is necessarily minus the derivative of the electric potential, then if the electric potential satisfies that the relation below, then it is a stationary solution of the Vlasov-Poisson equation. Okay? So, and you understand very well immediately that you have no problem in solving that equation. For example, if the density of rho, if the density of ion rho is equal to 2 pi, is a constant, that necessarily phi naught equals 0 is a solution. And then general case you study. All what I will look at in dimension 1, x is in the torus, meaning that it is the interval 0, 1 equipped with boundary condition. Okay? Okay, so we have a stationary equation. So you can plot a profile of the characteristic curves of this stationary equation. So the characteristic curves means that you need to solve the free transport. It is the integral curve of this operator v dx plus phi naught prime dv. And if phi naught, excuse me, is 0, is a constant, then the characteristic curve are just straight line. But if phi naught is not a constant, then you can have this kind of profiles, and you have a certain, it is closed, an electron hole or a closed loop or this kind of things. But essentially it is not looked at in the literature. Oh, I forgot to say that the Vlasov-Poisson equation, the nonlinear Vlasov-Poisson equation, is very famous nowadays because there were these very famous results by Moore and Villani some years ago on the nonlinear dynamics of this equation. But what I will do will be only linear equation. So it is a description of a family of stationary profile. And then in plasma physics, it is what is needed. You need to linearize around this stationary profile. So f, any function f, will be a stationary f naught plus a perturbation size epsilon. And just for convenience, you scale correctly the perturbation. You have the square root of f naught. There's no magic in it. It's just because it's a good scaling. Okay? And you do the same for the electric field. I remind you that if the homogeneous reference profile is non-homogeneous in space, then E naught is non-zero. In most cases, we look at homogeneous profile, then E naught is not zero, but in the general situation I will look at, E naught is non-zero. Okay, it will be more general. Then, okay, you turn the crank, you linearize the equation, and you write your equation for U, which is the perturbation of F in convenient scaling. So it is written below, dTu plus VDXu minus E naught dVu plus the perturbation of the electric field, F. Then you have the V. Why do you have V? Because you have the derivative of the Maxwellian. So necessarily you have a V. And then you have a square root of F naught. It is just the equation. It comes from the equation. But here I have decided to say that F, because I write the Poisson equation, I can solve F in function of U. Because I know if I linearize, dx of f is this integral. So I can solve in 1D equipped with boundary condition, with periodic boundary condition, and you choose an electric field which has 0 mean value. So you have no problem. This dx minus 1 is correctly well posed. And then it is just the 1D, 1V linearized Vlasov equation. And then you try to understand this old remark by Pierre de Gon. And then you say, what do I remark is that dTu plus VDXu, the transport part is fine because it is clearly an anti-symmetric operator. Then I have the V, the square root of F naught, they are just coefficients, say. But f of u, what is f of u? It is a certain integral operator minus 1, a certain derivative, okay, it is the primitive of a certain integral. And if you look at this operator, u that gives you f of u v square root of f naught, then you understand that, then you do not understand, then you check it is neither symmetric nor anti-symmetric. So it has no structure with respect to the most simple general theory. Of course, it is linear operator, but it has no structure. So what does it mean? It means that this 1D, 1V linearized Vlasov equation cannot be, is not member of this general family of Hermitian and bounded linear operator. You cannot. So you need to do a specific theory for this, and you need to check everything. And okay, and this is why it was an analogy and not an example. It is just because of this electric field, which in this form cannot be, is not symmetric and not anti-symmetric. But the key observation, and this is where it starts, is that if ever, instead of the Vlasov-Poisson equation, you look at the Vlasov-Ampère equation, because of course, all these come from Maxwell's equation on the top. So you can write Poisson equation to represent the electric field, but you can also write the Ampère equation. Of course, you need to check compatibility at initial time, but what you check is that you can write a system of two variables, u and f, which they evolve apparently differently. It's not exactly completely the case, of course. But the equation dTF is the integral of UV M dF. You have to remember that, okay, excuse me, what is M? M is just a notation for the square root of F naught because it will simplify. So it is M is a Maxwellian, but there is a dependence with respect to the reference electric field, the stationary electric potential, excuse me. So I write it M. You can think of it as a Maxwellian, but it's a Maxwellian, you know, little change in space, okay? But UM is the perturbation in F. So you really see that the second equation is the Ampere equation after linearization. And if you look at this system, clearly all operators are now anti-symmetric. The transport operator, the full one, is anti-symmetric, VDX minus E0, which is function of X dV. But also the coupling on the right-hand side is anti-symmetric for the pair of a node. What does it mean? It means that immediately you write this formal conservation of quadratic energy, okay, which is just a property of the equation. And now, because then you understand that written like that, there is a system that preserves a quadratic energy, and necessarily the system, because it is a linear operator, so behind, must be anti-symmetric in a way or another. Okay, and then you equipped all this now equation with some structures. Okay, it's natural to decide to work in L2 for the kinetic unknown U. So U of t will be a function of x and v, but in L2 of the torus across the real line for the velocity variable, times what? L2 0, 0, it means just because we need to add the fact that f has mean value 0. I do not describe this. I've decided to simplify the notations. But okay, but there's no problem about that. I will not discuss that. But then what you get is that formally U prime, I mean U is my pair of a node, is okay. So I know very well that I do not write the equation in the standard way, meaning that the imaginary number is not just in front of the time derivative. Okay, because I prefer. I apologize for that. But nevertheless, what is important is not what is important. What is important is H, the operator, which is not a block operator, matrix operator, is the sum of two operators, H naught and K. H naught is clearly, you see, symmetric. And K is clearly a perturbation. And immediately you understand that because it is a perturbation, you have to look at the nature of this perturbation. Is it compact? Is it Hilbert-Schmidt? Is it compact in V? Is it compact in X? But nevertheless, you understand immediately that now you can analyze everything with this in the context of this Hermitian unbounded operators. Okay, you check all the classical things. The operators are symmetric, but are they Hermitian? Yes. Okay, there is a technical difficulty that appears everywhere with this kind of equation, is that the Gauss law, I said Poisson, but it was the Gauss law, is that you have to satisfy initially, which is a technical condition on between f and u at t equals 0. The technical condition comes from it is the Gauss law, actually. It is propagated by the dynamics. We have similar things for Maxwell's equation. So Ricardo told me it is what is called the spectral property. But now, nevertheless, everything is on good, well organized, so that we can think of using classical scattering theory. So when I say classical scattering theory, I really mean the one that was developed in these very super classical textbooks, for example. It's Simon, Cato, Lax, and all this. It is always okay. The main question, as far as I understand, is always the same. I take a certain operator, capital H, which has this additive decomposition, and we would like to understand. And K is a perturbation of H naught. We'll have to characterize what kind of perturbation, and it is unbounded. H naught is unbounded, and K is small. We will see. except that clearly, excuse me, K is an integral in V. So there's no derivative in K, you see? There is an integral in V in the second part. In the first one, you multiply by M, but M is a Maxwellian, so it is clearly compact, no problem with that. So K is compact in V, but is not compact in X. This is really a fundamental property. Okay, so we say K is small so far. And then I decided to ask, what can I do if I open these textbooks and I try to apply the orthodoxy of this kind of things? We can try to calculate the spectrum explicitly, something we did with Ricardo on magnetized equation because it was the good way. We can have a look if there is some Moller operators of some truss class perturbation operators. Also, okay, all these classical techniques that are explained in these books. Okay, so now I'm still in my first part, and I will give you two examples why, in my opinion, this is a good question to try to see. Okay, so for example, so let's have a look back at this Vlasov-Poisson equation, but now homogeneous case. So E naught is 0 because phi naught is 0. So it is the same system I wrote, but simplified. And the question, okay, so now it is really much simpler, of course, because you can do Fourier in space, so you can decouple Fourier modes per Fourier mode, and you can have a look at the equations Fourier mode per Fourier mode. But nevertheless, you can ask you the question: is it possible that the operator this additive decomposition is it possible that it can be trace class? Because it is a fundamental object in scattering theory. So, okay, here the answer is super easy to look at because you just do the Fourier decomposition and you look at the trace class, the Cato-Biermann characterization, the Cato-Biermann. So you look, so now H becomes HK because it is before it was VDX, but now because of course we have a Fourier mode, it is VK, isn't bounded because V is an unbounded variable. Okay. And HK is the total, so the perturbation is the difference. So it's very clear that TK, okay, so we know we use Z, which is complex number, N, which is non-zero integer. So it is very clear that the perturbation is trace class individually because here it is finite dimension. There's no difficulty. So actually, it is the simplest proof I have of the linear Landau phenomenon. You do this decomposition, you observe that the perturbations are trace class, then immediately that you understand that the continuous spectrum is preserved, you do basic exercise and you have no singular spectrum, and necessarily you have this kind of Riemann, Lebesgue-Riemann formulas, which explains that the electric field tends to 0 at infinity, which is actually one of the main results of the linear Landau theory. But the interesting thing is to look at the greatest eigenvalue of this TK mode per mode, and you check. It is a basic, very standard calculation. Look, you can obtain all the asymptotic values of these behavior of these eigenvalues. That the largest eigenvalue of TK is actually like 1 over K. Okay, you look at my last inequality here, it's 1 over K. So what does it mean? It means that, of course, there's no problem to look at TK individually, but nevertheless, if now you reassemble the total operator T, and because every TK has eigenvalue 1 over K, then you understand that the trace class, the trace of operator T, is as a logarithmic divergence. So it's not trace class if you do the calculation like that, but it is almost trace class, which is the indication that it is essentially a technical thing. I will elaborate on that. And the second thing that I need to explain is that, to my great surprise, when I decided to look, okay, so one of the consequences of these trace class properties are, okay, existence of wave operators, But actually, there are also Moller theory, the Moller operators. And actually, I really recommend to look at this paper by Morrison, the 2000 paper. Actually, I really discovered these operators in 2014, completely independently. And actually, okay, you look at this operator, you have a function of x and v, and what you do, you have this operator, I call it L, minus the second derivative of u plus q. Q is the principal value of a square of the Maxwellian, so okay. Minus Vm, so okay, so you have function, then the principal value of u against m. Okay, so okay, the difficult part is to imagine how to construct this operator L. But the key thing is that if u satisfy my Vlasov equation, my linearized Vlasov equation with the Gauss law, and physically there is no choice, the Gauss law is always satisfied, then you check, this is just an algebraic verification, extremely easy, 4 lines, then H, which is equal to Lu, is a solution to the free transport equation. So actually, it is exactly what, well, exactly, I don't know, but it is exactly one of the things that Moller operator or Moller wave operator or generalized Moller wave operator are for. I mean, you apply the operator and it simplifies the equation somehow. So, well, in other words, if you take an initial data U naught below, you apply L, you solve the transport, then you inverse L, then you have a solution of your linearized Vlasov-Poisson equation. So it means that in terms of the formal operators, you have the propagator of H is L minus 1, the propagator of H naught, excuse me, L. Okay, the I is everywhere because I want to play with Hermitian operator, and VDX is not Hermitian, it is anti-Hermitian this way. So, but if you differentiate, then immediately you have this property LH is equal H naught L. And actually, it is one of the characterization of a generalized wave operator by Yaffe. So it is extremely, it was very intriguing to me. How is it that the wave operator, the Moller operator exists? But of course, it is just because the scattering theory, all these equations can be rewritten in terms of the scattering theory. So it is essentially my first part. So, okay, so I need perhaps not to spend too much time for the second one because it will be more technical. So I just want to describe two results, but essentially one result. When I decided to really use the scattering theory. So I said, okay, is it possible to prove that in case of a non-homogeneous perturbation, there is essentially no result in the literature on homogeneous perturbation of an homogeneous profile, excuse me. So now phi naught is non-zero. Okay. So I look at this system and I would like to prove it is trace class. Is it possible? And if I try to do this, what's going on? So this is the part I don't want to. So I said that in 1D, in simple case, Vlasov operator was almost trace class. So of course you need to manipulate before trying the trace class to obtain the trace class property. So a possibility is to do this trick. You take Q, you take F, and you multiply by gamma M. Actually, honestly, I don't know. Okay, the algebra is clear, but I don't know where it comes from. So, and you check for a weight gamma such that the L2 norm of U plus the L2 norm of F, which is preserved by the operator, is equal to the L2 norm of W, which is a new kinetic variable. Okay? And if you turn the crank and you find that if gamma is solution of this Fricati equation, then which has a solution on the torus, there's no problem. You can really check by a shooting method. You have absolutely no problem. You have uniqueness, existence, and uniqueness of gamma. Okay. And for example, if phi naught is 0, gamma probably is equal to is a constant, and in other case, okay. And then okay, this is the algebra. But it is important. Why? Because it means that you can probably write the operator for this reduced variable W, and now you will not have this this go slow, initial go slow. Actually, it is a way to hide the fact that the go slow is spectral. So now with this, you don't care about this, and you can do your decomposition. And you do this, and you write everything in terms of operators, and without surprise, dt of W it is equal to a new I. There's a new Hamiltonian, curly H, and this curly H is the sum of H naught, which is still the same, the free transport, plus plus integral operators, and but it is autonomous. You don't need anymore any F. So now you have an autonomous equation with these operators, which is equivalent to your linear Vlasov-Poisson equation. So what you see, you have gamma, but gamma is a predetermined weight, so there's no problem. So you see that is integral with respect to the velocity, and once again, but no integral with respect to x. So once again, these kappa curly operators are compact in V, but not in X. And also they are finite kernel. It's clear because it is sample and kernel integral against a Maxwellian weight in velocity. So if ever what's done, actually it can be described with effect in terms of the Hermite function, if you like, but it's not really important. The only thing which is important is that kappa and kappa 2, clearly kappa 2, there are two integrals, so it is super compact. So kappa 2 is finite dimensional, so kappa 2 there's no problem. So kappa 1 is the one that you have to look at. So you try to check the trace class between H and H naught, or between H naught and the perturbation kappa 1. So you look at this. And then you assemble this T star T st, and now it ends up that you have to look at the spectral problem with these operators. And because you can just project in the orthogonal of the kernel, which is evident, because in the kernel you have 0 eigenvalue, then you end up with a pair of two integral, it is the lemma, the second lemma, of two integral operators, and then you have two functions of x, a and b, and if ever they satisfy this system, gamma exponential phi naught t2, gamma exponential phi naught t1a equal lambda a, and then you cross, excuse me, perhaps I made, oh no, they're almost the same. The difference is that the second one, it is T2 before T1, and the other one, it is T1 before T2. So essentially, they are the same. Then this is the only thing that you have to look at. Okay? And then you check that these T1 operators, they have clearly a symmetric or Hermitian structure. So, but you have to, you see, you take a function of x, you multiply by a function in V, you solve free transport plus z square, free transport to the square plus z square, and then you calculate once again the mean. And then this is the kind of operators that you have to look to analyze. And clearly it is known that, of course, it is the regularity, the gain of regularity of the operators, because they are symmetric, they can be transferred into rate of convergence of the eigenvalues. So what you check is that without any problem, T2, you gain two derivatives. So it is excellent operator. So you have no problem so typically the eigenvalues of T square will goes to 0 at a weight 1 divided by n to the power 2. So to check the trace class property, no problem at all. So now the real problem, and this is exactly what I want to pinpoint, is T1. For T1, you have a real problem. Because T1, but what you can prove is T1, you have a gain of regularity for the 1/2. And what I really want to explain, to tell, is that the fact that to prove this, okay, so you look at the integral, so okay, so b, for example, b is a function of x, and then you multiply by a function of v, you solve this kind of operator -1, and then so it is a coercive operator. You have not that much problem, but you have to do it nevertheless. Okay, you can play with the equation, but actually there is a very famous Now, old results, it was proved in the 80s, I think, 80s, or I don't remember when exactly, by Gall, Santis, Pertam, and Pierre-Louis Lyons. And these results are exactly on compactness by integration. And it just explains to you exactly the gain of regularity when you look at these kind of things. So this gain of regularity for T1 is exactly due to very famous results on a fundamental result on gain of regularity in transport integral differential equations by Gall, Santis, Pertam, and Lyons. And here on below, you see that you have a gain of regularity 1/2. So why it is only 1/4 in the lemma? It is 1/4 because actually when you have, it is 1/2 is if E naught is 0, but if E naught is not 0, because it is the more general case, then actually François Gols just told me, I really thank him for that, that actually a very famous result by Dipernat and Lyons is exactly the key tool. And it gives you the gain of regularity 1/2, and then you prove the trace class property. So okay, so what I wanted to say is that really some fundamental result in transport equation can be used to prove the technical, of course. The trace class property is fine, but then you have to prove some analytical property for the operators that you have. Okay, and because it's okay, then it was a published result published 4 years ago. Then you can characterize, and then you have the trace class decomposition. So the wave operator exists, and you have an isometric bisection between the absolutely continuous part of the spectrum. And that's okay because it describes what's going on if you perturb a free transport operator by an operator which corresponds to coupling with electric field. And actually a much, okay, it's just, wait, okay, okay. So, excuse me, the first result is a structural result in terms of decomposition of space. And the second result, I was able to go far beyond in terms of the physical description. Because if you have technical but very natural hypothesis for this kind of non-homogeneous profile, then what you can prove is that actually F, because you have integral representation, you compute completely the Lippmann finger representation, and then you have a full complete representation of the solution, and you can prove that thanks to Riemann-Lebesgue integral, the electric field tends to 0 in the long time, which is but with no rate of convergence, but you can prove it. You prove it, and actually this is exactly it is one of one part of this famous result by Landau on the linear Landau damping. So you can so thanks to scattering theory, it's possible to extend to non-homogeneous profile. What time is it? Perfect. So now I am starting my last part, so that's fine, which is much more exploratory. Okay, so we did a specific work with Ricardo on the incorporation of magnetic field. So all what I have explained in the talk was on purpose only for equation in 1D for the space variable. So question cannot be generalized to multi-D. Okay, clearly, if the reference profile is homogeneous, so E naught is 0, phi naught is 0, there's no problem because you have separation of variable. So the main question is it possible, for me actually, so you really have to go back to your equation in multi-D. You have to write your Ampere equation because it is needed to apply this methodology. Instead of Vlasov-Poisson, I need systematically to write Vlasov-Ampere because the structure is much more evident. It's absolutely evident with Vlasov-Ampere, especially to use this additive decomposition, H is equal to H naught plus K. And then, but then, okay, then you have to look to construct your stationary profile. So once again, here we decide that in velocity it is a Maxwellian. Actually, it is a restrictive hypothesis. I will show you my just with numerical simulation what's going on if you change the profile in velocity. But you can do essentially the same. And here, okay, so honestly, I think it is still an open problem to generalize what was done to multi-dimensional equation. But structurally, there are some parts that can be done. So it is a strange decomposition. Strange, okay, it is possible to once again to hide the Gauss law by constructing this W kinetic variable. And actually, we end up with a system, with an equation, an autonomous equation, dtw plus free transport minus IAW equals 0. And once again, A is an integral operator. But if you look in detail, now it is an integral in V. So once again, it will be compact in V at the end of the day. But there is one derivative in X. There is a gradient. You take a primitive of you have to solve a Poisson equation. So now it is more regular by a factor 1. But if you look at here how the operator L was constructed, you count the number of derivatives and okay, how much, how many? Yes. So okay. So the exterior delta in terms of the number of derivatives, there is a minus 1/2 and a plus 1/2, so it is 0. And on below, in the middle, you have minus delta. You take a square root, so it will give you. It's okay. So L is homogeneous to a gradient, one gradient. It counts for one gradient. So what it means? It means that L minus delta minus one gradient. It is an operator of say degree. I will say of degree 0 in X. There is no derivative and there is no primitive. So once again, this operator excuse me, is compact in V, but is absolutely not, there's no regulation at all in X. So it is an open problem to do the work and to characterize this thing. Probably it is technically extremely interesting, but I have not done that. So now completely, as I said, and it is completely new to even for you, Ricardo. So very recently, there was this thesis of Victor Fournet at CEA, and it was much more oriented to an applicative problem, which come from an engineering problem. Actually, it is really an engineering problem. It is not written as an academic, an abstract, or very theoretical problem. Very engineering. Actually, okay. So you just You just completely forget about the math, and you look at the problem, the physical problem. So you have particles, but they are not exactly particles. They are more droplets or grains, so much bigger than a particle. It's not an electron, it's much bigger. So it is called in the engineering community the theory of sprays. They have a lot of problems to model the sprays. So you can have a spray in your diesel engine, in your car. This is my first picture. You can have a medical spray or a spray with perfume, okay? But okay, of course, it's very important in the market, this kind of thing. But you can also have sprays which are more grain of sands in pipes, in pipelines. Actually, if the oil in a pipeline, actually it's very dirty. You have a sand everywhere, and you have a continuous, of course, the flow. There is a flow, so okay. So clearly the grain at the end will be described with a kinetic equation, okay? And there are even more. It's not part of what I explained before, but in the engineering community they have this kind of it's a very recent experience where you have some grain that fall below, and here there is a shock wave because it is a way to characterize things, these complex flows. And actually, you try to characterize these things. So you see, it's absolutely not small particles. It's really droplets or grains. And but also these droplets or grains, they are in a gas or in a fluid. So what you look at in terms of models, and it is a model by Laurent, a family of model which is very much described in the works by Laurent de Villers, Laurent is also extremely strong name in kinetic theory. He's also a good friend, but it is another story. And you see the kind of equation, it's not Vlasov-Poisson equation. So okay, it is the simplest kind of equation. So you have thin sprays for medical sprays or thick sprays. Thick sprays, it is when the droplet is kind of big enough so that it can take some room in the infinitesimal volume. So what you need for a basic model is the following. You start with two equations with your fluid equation. Oh, you see, absolutely no Maxwell's equation. Your fluid equation, rho is the density of the fluid or the gas. Alpha is the room left by the particles. Alpha is 1 minus the integral of f. Here there is a mass, but this mass is more a volume. It is a reference volume. They always okay. So think of alpha as the room left by the particles to the fluid. And then you write your standard barotropic equation. But of course you need interaction between the particles and the fluid. And there are two ways that the particles are coupled with the fluid. The first one is that by alpha, because alpha, you need to calculate this place. If for thin sprays, alpha is always equal to 1. For thick sprays, alpha is in between 0 and 1. Okay? And there is, also, of course, the force exerted by the particle. So it is called gamma. The integral gamma f dv is the force exerted by the particle on the fluid. And this force is gamma is defined as the gradient of P, the fluid pressure, and there can be some friction. There can be some friction. Actually, for the scattering theory to be effective, the friction must be 0. So please, I wrote the friction, but for all what I will explain later, this star will be 0, which is not super physical, but okay. And then you need then you have your kinetic equation to explain how your particle move in the kinetic phase space in this x and v. Okay. So okay. So actually we had this recent paper which is analog of linear London damping. It is coupled Vlasov-Poisson system for 6 sprays. And the key observation for us, it is exactly what I explained. We did exactly the same. We say, okay, assume that we have an initial distribution of particle, which is, okay, assume it is a Maxwellian, mathematically is fine, but okay, physically, okay. There are some cases where you can argue it is reasonable, so let's assume that. No friction, this is what I said, the mass, or the reference mass or reference volume is set to 1. Everything is homogeneous in space for simplicity. Alpha naught is constant, non-zero, fine, okay, it disappeared actually. And what you end up is a system. So now you do exactly the same kind of scaling, and J1 is a function of T, X, and V. Huh? J1 is the perturbation of the density of particles with the same kind of scaling, because you have the square roots. And actually, it is more, if you look, it is a linear wave equation, dt tau1. Tau1 is the inverse of the density. Tau is the inverse of the density. So tau1 is minus rho1 divided by rho0 square. But what is important is that the first block, you see, you have a linear wave equation. It's normal because you are in a fluid. So you have acoustic waves. So this block is for acoustic wave, everything rescale. And then you have the coupling with the particle. And it really comes from the alpha. It's really for. And if you look at the structure of the block operator that you construct, you see it is exactly as it was done before. Of course, there is this transport part, V dx. There is where they are. Okay, here it is because there is decomposition Fourier mode per Fourier mode. Okay, so this thing is just a K. And if you check, you have a K everything because you have derivative everything, but it's not what is important. What is important is you have this kind of, if you look just as the matrix, which is in parentheses, between parentheses, it is a bounded operator except for this one. So once again, you have this decomposition I have explained. So H, once again, is H naught plus a perturbation. And actually, you check all the theory, and you check that you have all this decomposition, and we have explained that with Victor Fournet for his thesis, and actually at the end you have that you characterize the fact that all the space or the L2 space it corresponds to the absolutely continuous is associated to absolutely continuous part of the spectrum. So there is only absolutely continuous part of the spectrum. And then it explains that, of course, the solution tends weakly to zero, thanks to Riemann-Lebesgue. So essentially, it explains that τ1 and u1 square, which is the acoustic energy, tends to zero. So this result is just, in my opinion, the same, exactly the same as the linear London damping when we say the electric field tends to zero, because there was the same kind of phenomenon. But now it is the acoustic energy. So it's not the electric energy, but it is the acoustic energy. So you have to imagine that if in this situation, if we could hear the sound produced by these particles in this kind of flow, we will hear something that goes to zero. And of course, it means that all the energy goes to the particle. So then there is this extremely interesting thing, because I have not said that, but in the classical theory of the linear Orlando damping, not only you prove that the electric field tends to zero, but you have a rate of convergence. Why? Because actually you calculate with the Landau technique, it was different. But actually, they are the poles of the resolvent. You really have to transfer, but the language is not the same, but at the end it is the same, thanks to the papier of Pierre de Boom. And then you look at the system that I have looked at, and you do exactly the Landau. We decided to do it more with a physical notation. So we decided to look at the dispersion relation and to do the Landau trick in terms of the explaining in what part of the complex plane you have to look at the poles. Okay. And then you calculate the roots of this resonant equation. F naught is you have it. F naught is the Maxwellian. So the root is omega. Actually, it is very close to the dispersion relation for the Vlasov-Poisson equation, but it is different. And actually, this is a numerical result by Victor, where in orange you have omega is a complex value. Okay, it has I never know. It has negative imaginary part. So it goes to zero plus this kind of arches that very classical that we have in linear Landau. So in orange, it is the theoretical prediction, meaning we solve this, we calculate the pole, and in blue, it is something that comes from the numerical solution with a dedicated scheme of the full system. And the agreement is excellent. So what it means? It means that not only the theory is okay, but also it predicts in certain situations extremely correctly the dynamics of a very nonlinear system, which is an excellent news, of course. So it is a justification, a posteriori justification, that it is a good idea to linearize the equation. So okay, it is the electric, it is the velocity that goes to zero, and it is the difference to the density that goes to zero. And for those who know, this is a classical. This is the same calculation, but here you solve the dispersion relation for the Vlasov-Poisson equation. So we have this very, very famous thing, which before was not explained within scattering theory, but now we can do it. It's an exercise. Okay, so if you would like to ask what is the reason why the theory for Vlasov-Poisson pair can be extended to 6 sprays, the reason is extremely easy. It is due to the fact that if you look at the kinetic equation, they are pretty much like the same. For example, the kinetic equation for a thick spray, then you have this force gamma, which is minus the derivative of the pressure, the gradient of the pressure. And for plasma physics, it is the electric field, but the electric field is minus the derivative of the electric potential. And then you understand there is an immediate similarity, and then you have to check all other details. And this is why it extends. So it is, okay. So here it is my movie. My movie is, okay. So now you can ask, what's going on if we in plasma physics, it is very classical. So it is a simulation done by Victor. If we assume that the reference in velocity is no more a Maxwellian, but can be a Maxwellian with two bumps, something like that. So, for example, the color plot is exactly that. So it is in the coordinates are x and v, and it is the magnitude of f at time t equals 0. So if you want to understand what is f in velocity, you do a vertical cut, and you see that you have a two bumps profile. So it is like so for example, if you take a Maxwellian and you multiply by v square, you obtain this profile. Okay. And it is called, and if so, it means that initially you have particles that have positive velocity and particles that have negative velocity, and it is called the two stream instability. So now all what I did cannot be done, and you will have completely different behavior. So it means that there is nothing like the linear Landau damping, and the electric field, no, excuse me, the acoustic energy does not go to 0. And here it is a movie on what's going on. So what you see, initially you see nothing because we had just a very small perturbation, but on below you see the perturbation of tau and the perturbation of the velocity. And instead of going down, they go up. Why? Because it is linearly unstable now. It is extremely interesting, of course, for the physics. And then, but now we solve the full nonlinear system. So initially, you can explain things just with linear tools or objects, because clearly it is a linear behavior. So still, up. And but now, of course, it starts to become very nonlinear. So okay, so this is now you see the perturbation that grow, and clearly now there is saturation of the modes. And there is this very super nice things that I wanted to show to you. Perhaps now we start to have some shock wave. We don't know because it is a fluid equation. It's possible. We don't know exactly what are these waves, but they have a very complex structure, and it's extremely difficult to analyze, of course. So I stopped this one. So and now I just give my conclusion. Where is it? Yeah. I just give my conclusion. Where is my, okay. My conclusion is the following. Activer le mode plein écran. I think it's done. I'm done. Okay. So exactly. So my talk was on the fact that we can just rewrite all this kinetic Poisson equation or Euler-Poisson equation, a kinetic Poisson equation as a kinetic Poisson-Ampère equation, but you can also do the same with Euler instead of Poisson-Ampère. Actually, what is important is to couple the kinetic equation with a macroscopic equation. This is what it says. And in certain cases, it can be rewritten exactly after linearization within the theory of Hermitian and Bardet operators. And then, okay, you can have an explanation of linear damping and similar phenomenon, which now is classical. Clearly, very clearly, it's just impossible with the tools that I have explained to address the nonlinear case. Okay? And I'm done. Thank you very much. I have finished.
Okay, thank you. Thank you very much, Bruno, for very interesting talk. Questions, please?
Well, I have a couple of questions. First, going back to the multidimensional case, after the variables, are you hoping to prove a trace class condition there?
Excuse me. Yes, it was exactly what was the objective of this starting of this algebra. Exactly. So what does it mean? It means that you can you need to address it now is in an unbounded domain, because it is what is interesting. So it means it is more equation at the level. Okay, it's not gravity, but it is perhaps it is more equation at the scale of a star. I don't know exactly.
You mean for galaxy dynamics?
Exactly, this kind of things. Okay.
And then the second question, well, in Landau damping, we say that the electric energy is transferred to the electrons, say to the particles, right?
Yeah.
But here in this spray situation, so all the acoustic energy go to the particles in the spray, or how is it physically?
Okay, actually, I have just no. So this is a very new result that we have obtained with Christophe and Victor. So now we have to discuss that with the physicists, with the people in charge of the experiments. Or I don't know if they have experiments or the new apples. Okay. So, but the theory is quite clear. No, okay. So what I did not say is that if you want to describe really something which is reasonably physical, it's much better to add friction. And if you add friction, you add an explicit dissipative mechanism in the set in the equations. And if it is an explicit dissipative mechanism, it cannot be an anti-symmetric operators that only describes the dynamics of the problem, because there must be some damping, some explicit damping, or okay. And then so what we did in our paper, we tried to write the dispersion relation. No, it was not. No, yeah. So actually when you try to write the dispersion equation, I mean, the equation are not very friendly. Actually, you're not able to do it. You have a complicated equation, and we did some linearization to try to obtain some numerical values. Okay. So my message is, I don't know, I'm not sure we will find some people in the experimental world that will be able to discuss our experiment with us without friction. So because it is more physical, so clearly, because you can imagine particle in a fluid, clearly there is friction.
Well, maybe we talk about that later, but there is an extension of scattering theory to systems with dissipation, with friction.
Yeah. I know, but in the first part, we really try to do it step by step, making the basic comparison with this basic
Certainly,
technique.
that's a very good idea to take first the frictionless case.
Yeah, then and also to obtain intuition between doing these more involved math.
Right. Okay, we can talk about that later. So, well, thank you, Bruno, for your beautiful lecture.
Thank you.
Thank you. More questions, please.
I would like to ask a question. So you mentioned that the perturbation is not exactly trace class, but just on the borderline.
Yeah.
So the usual trace class scattering theory does not apply. Do I understand correctly?
Yeah. So
yeah. So instead, I mean, of course, trace class condition is not a necessary condition for the existence of Miller operators.
Yeah.
But so in your case, the Miller operator, does it really exist in the usual classical case, or?
So for non-homogeneous profile, I don't know. The only thing I am able to do is this restrict by hidden. But I can tell you what I really think is the fundamental reason. Okay, there is something that I cheated. No, I did not cheat. Okay. So there is clearly this decomposition of the operator H is equal to H naught plus K. And as I said, the Gauss law must be, of course, satisfies at t equals 0, and it is propagated by the equation. It is propagated by H. But when you do the additive decomposition, it is not propagated all the time by H naught. So what does it mean? It means that if you do this decomposition, you are somehow doing dirty things about the Gauss law, And it is much better this is why it is much better to try to rewrite the equation with a convenient unknown, so you don't have any more physical, mathematical, or philosophical problem with respect to this go slow, and then I observe that there is no problem. So I think this is related to that.
This go slow, can it be interpreted as a certain constraint on the space? I mean, so
exactly. You're perfectly right. You're perfectly right.
Yes.
So if a scattering theory, I know there is some, is able to incorporate such constraint in a natural way, it will be a tool that will be
yeah.
perfect.
So there is something like a two-space
Exactly.
scattering theory.
Exactly. I looked at this theory when I was asking myself these questions, but suddenly I found this trick. And this trick of having this new variable that I call W, which is made as a linear combination between U and F, and which is equivalent to U and F. Okay, this is the algebra that gives, and then suddenly I didn't need any more this double space. I don't remember.
Okay, so you just compute the Miller operator by hand instead of using a theory. That is,
exactly.
Can I say this?
Yeah, exactly.
Okay.
With this reduction, then the problem disappeared, but fundamentally, I have not understood the. Okay, there is probably something more.
So in particular, is your Miller operator unitary in some way or not really?
For the initial problem, so in my paper, yes, in the sense that I have described the Miller operator for the reduced problem, and then because there was a bijection, but a complicated one, I have described the structure, how it is transferred to the initial problem. Yes, I did that.
So there is an underlying scalar product because you.
But I agree with you. I agree with you. But fortunately or unfortunately, I don't know. This simple trick was enough to get rid of this fundamental problem.
Okay, thank you.
Thank you. More questions? If not, thank you again, Bruno, and we close our today's session. Thank you to everybody.
Let me remind that we have a session tomorrow at 9. And for those who are new, who did not join earlier, well, all the lectures, you can see them in the YouTube and Facebook channels of EMAS. You have the link in the email you got to join the Zoom session. Okay.
Thank you. Goodbye. See you tomorrow.
Bye-bye. See you tomorrow.
Bye-bye.
See you tomorrow.
So bye-bye, Bruno. Bye-bye, all of you. Well, I will close the session then.